we shall now solve problems on D'Alembert's ratio test. To solve problems on series which have factorials, generally we use D'Alembert's ratio test, PDRT, that is problem on D'Alembert's ratio test. Test the convergence of the series 2 to the power n into n factorial divided by n plus 3 factorial. So this problem, this series contains factorial notations. Therefore, we will apply D'Alembert's ratio test to find the nature of or the convergence of the series. Let us consider un be the given series. Therefore, un is equals to 2 to the power n into n factorial by n plus 3 factorial. We are going to find the limit of un plus 1 by un. Therefore, what is un plus 1? In un, wherever n is there, replace n by n plus 1. Therefore, un becomes un plus 1. That is equals to 2 to the power n. Therefore, replace n by n plus 1. So, 2 to the power n plus 1. N factorial. Replace n by n plus 1. So, n plus 1 factorial. Divided by n plus 3 factorial. What is n? We have to replace n by n plus 1. Therefore, it is n plus 1 plus 3 factorial. That is equals to 2 to the power n plus 1 into n plus 1 factorial by n plus 4 factorial. Now, let us find the limit of the ratio. That is un plus 1 by un. So, limit of this is nothing but un plus 1. That is 2 to the power n plus 1 factorial divided by n plus 4 factorial whole divided by un. Since un is in the denominator, we have to write its reciprocal. That is, we have to write the reciprocal of 2 to the power n into n factorial by n plus 3 factorial. That is n plus 3 factorial by 2 to the power n into n factorial. So, this is un plus 1. This is by un. That is equals to, we can write 2 to the power n plus 1 as 2 into 2 to the power n. And n plus 1 factorial can be written as n plus 1 into n factorial divided by this n plus 4 factorial can be written as n plus 4 into n plus 3 factorial into n plus 3 factorial divided by 2 to the power n into n factorial, so that this n plus 3 factorial get cancelled. This 2 to the power n also get cancelled. This n factorial get cancelled, and hence we are left with only 2 into n plus 1 by n plus 4. Therefore, that is equals to limit of 2 into n plus 1 divided by n plus 4 as n tends to infinity. Now, let us take n out from n plus 1. Similarly, in the denominator, take n out from n plus 4. So that is equals to limit of n tends to infinity 2n into 1 plus 1 by n divided by n into 1 plus 4 by n. This n get cancelled. Therefore, we have limit of un plus 1 by un is equal to limit of 2 into 1 plus 1 by n divided by 1 plus 4 by n. We are going to apply limit. Wherever n is there, replace n by infinity. What is the value of 1 by infinity? 0. What is the value of 4 by infinity? 0. Therefore, when you apply limit, we are getting 2 into 1 plus 0 divided by 1 plus 0. 1 plus 0 is 1. So 2 into 1 by 1, that is equal to 2, which is greater than 1. Greater than 1. The limit of un plus 1 by un is normally taken as L. L value is 2, which is greater than 1. What is the statement of D'Alembert's ratio test? That is, if series un is a series of positive term and if limit of un plus 1 by un is L, then series un converges if L is less than 1. Diverges if L is greater than 1. The test fails if L is equals to 1. But here, what is the value of L? L value is greater than 1. What is the limit of un plus 1 by un here? It is 2. That is L value is 2, greater than 1. And hence, by the statement of D'Alembert's ratio test, the series must diverge, because the statement says that whenever the limit is more than 1, greater than 1, the series must diverge. Therefore, by D'Alembert's ratio test, the given series is divergent. Test the convergence of the series 2 to the power n into n factorial divided by 2n factorial. In this problem also we have factorial notations. Whenever a series with factorials, generally we apply D'Alembert's ratio test. Let us take the given series as series un. Therefore, un is equals to 2 to the power n into n factorial by 2n factorial. Let us find the value of un plus 1. To find the value of un plus 1, replace n by n plus 1 in un. Therefore, un plus 1 will be 2 to the power n plus 1 factorial divided by 2 into n plus 1 factorial. That is equals to 2 to the power n plus 1 factorial divided by, let us multiply by 2, it is 2n plus 2. Therefore, 2n plus 2 factorial. Now we have to find the value of limit of un plus 1 by un. Therefore, taking limit on both sides, limit of un plus 1 by un equal to limit of 2n plus 1 into n plus 1 factorial divided by 2n plus 2 factorial. This is whatever written in blue color is un plus 1. What is un? Whatever written in red color, that is 2 to the power n factorial by 2n factorial. Therefore, since un is in the denominator, we have to write its reciprocal. The reciprocal of 2n into n factorial by 2n factorial is 2n factorial by 2n into n factorial. That is 2n factorial by 2 power n into n factorial. Therefore, the next step will be, here we write 2n plus 1 as 2 to the power n into 2. So that this 2 to the power n and 2 power n can cancel. This n plus 1 factorial can be written as n plus 1 into n factorial. So that the n factorial, this n factorial get cancelled. Here 2n plus 2 factorial can be written as 2n plus 2 into 2n plus 1 into 2n factorial. Therefore, the 2n factorial into 2n factorial get cancelled, and hence we will be left with 2 into n plus 1 divided by 2n plus 2 into 2n plus 1. Rest are all term get cancelled. Let us multiply by 2 so that it is 2n plus 2. We also have 2n plus 2 in the denominator. Therefore, these two terms get cancelled and we are left with only one factor, namely 2n plus 1. That is limit of 1 by 2n plus 1 as n tends to infinity. Now we have to replace n by infinity. Therefore, it is 2 infinity plus 1. What is 2 infinity plus 1? Infinity. Therefore, 1 by infinity. What is 1 by infinity? 0. What should be at 0? 0 is less than 1. Therefore, by D'Alembert's ratio test, whenever the limit is less than 1, the series must converge. Therefore, by D'Alembert's ratio test, the given series converges. Determine whether the series n minus 3 by 3 to the power n converges or diverges. That is, we are going to find the behavior of the series or the convergence of the series n minus 3 by 3 to the power n. Let us consider an is equals to n minus 3 by 3 to the power n. Then what is an plus 1? An plus 1 is replace n by n plus 1 in an. Therefore, we get n plus 1 is equals to this n is replaced by n plus 1. Therefore, n plus 1 minus 3 divided by 3 to the power n. This n must be replaced by n plus 1. Therefore, it is an plus 1 is n plus 1 minus 3 by 3 to the power n plus 1. By ratio test, what does the ratio test say? It says the limit of un plus 1 by un is L. Now here un is taken as an. You can take nothing wrong in it. Nothing wrong in it. Therefore, limit of an plus 1 by an is equal to limit of whatever we have written in blue color is an plus 1 and in red color is an. Therefore, an plus 1 is n plus 1 minus 3 divided by 3 to the power n plus 1. An is n minus 3 by 3 to the power n. That is, n plus 1 minus 3 is n minus 2 divided by 3 to the power n plus 1, and we have to write its reciprocal. Therefore, it is 3 to the power n by n minus 3. Here we have 3 to the power n. Here we have 3 to the power n plus 1. This 3 to the power n plus 1 can be written as 3 to the power n into 3, so that this 3 to the power n, this 3 to the power n get cancelled, and hence we will be left with only 3 here. Therefore, limit of n minus 2 by n minus 3 into 1 by 3. Apply limit. Before we apply limit, what we do? We try to eliminate all n or the powers of n, and we try to get factors as 1 by n or a by n. Therefore, take n out from n minus 2. Similarly, in the denominator, take n out from n minus 3. Therefore, when you take n out, we get n into 1 minus 2 by n. Here n into 1 minus 3 by n into 1 by 3. This n get cancelled. Therefore, when you apply limit, 2 by n tends to 0. 3 by n also tends to 0, and hence we get 1 minus 0. Divide by 1 minus 0 into 1 by 3. That is 1 into 1 by 3 is 1 by 3. 1 by 3 is less than 1. Less than 1. That is, the limit is less than 1. Therefore, according to D'Alembert's ratio test, when the limit is less than 1, the given series must converge. Therefore, the given series converges by ratio test.